Hello and welcome to week 2 of Schrödinger's course, a course that may or may not exist. The door will be opened when these videos stop appearing for good, but that could be years in between, who knows? Well, that's not important. So, what are we doing this week? So, the birth of quantum physics, quantum mechanics, really took place on December 14th in the year 1900, when a fellow by the name of Max Planck presented a paper. And this is my description. It's not a perfect description of what happened, but if I write this up, this will be in there. So I don't know if you're familiar with Xenos Paradox. It's an oldie but a goodie from the old Greek world. Basically, and I'm summarizing or making it my own, paraphrasing Xenos Paradox even here. Let's say you're trying to shoot an arrow at a target. Well, before the arrow can get to the target, it has to go halfway to the target. And before it can get halfway to the target, it has to go halfway to halfway, or a quarter of the way. And before it can go a quarter of the way to the target, it has to go an eighth of the way. And before it can go an eighth of the way, it needs to go a 16th of the way, and so forth and so forth. And so what you find is the arrow can never actually leave the bow, right? Because it has an infinite amount of space to traverse before it can get to the target. I mean, and it can't go through an infinite space. I'm not that strong. And so basically the arrow can never even leave the bow. So this is obviously not true. It's Zeno's paradox about, crossing infinite. Now, what does this have to do with Max Planck and the quantum? Well, so it was pretty much assumed that energy, to get from energy 1 to energy 2, it had to go through that infinite amount of energy in between energy 1 and energy 2. So it had to go between energy 1 and energy 2, it had to go halfway, and then it had to go a quarter way, and it had to go an eighth of a way, it had to go, 16th of a way, and basically the energy, how could it ever even get, to from 1 to 2, because it had an infinite amount of thresholds to cross. And I hope to, maybe 2 weeks from now, we'll see, might be next week, but probably 2 weeks from now, talk about what's sometimes called the ultraviolet catastrophe. It basically was a consequence of what the understanding of black body radiation was. A black body is a hypothetical body that absorbs all frequencies, all wavelengths of energy and light, that electromagnetic radiation that come on it. And the current understanding in the late 1800s had the consequence of basically it becoming so irradiant that basically it was emitting infinite amount of radiation, which of course would have killed us all. But anyway, this didn't happen, and so it was a problem because the theory didn't match life or experience. And this is what Max Planck was trying to wrestle with. Max Planck, by the way, I've been reading a little bit in this book, The Quantum Moment, by Robert Crease and Alfred Scharf Goldhaber, or Goldhaber. I don't know how it's pronounced. This book came out in 2014. Seems to be a pretty good book. How Planck, Bohr, Einstein, and Heisenberg taught us to love uncertainty. It's written by a physicist and a philosopher who paired up. So far, it seems to be pretty good at explaining things to little old me. So it's helping me. But it has a picture of Max Planck here on page 35. I don't know, can you see that? There he is, Max Planck. He was 42 when he presented this paper, December 14th, 1900. It didn't get a lot of acclaim. This is the interesting thing. In retrospect, we realize December 14th, 1900, the whole world changed. The world of physics changed. Everything changed. But at the time, it wasn't that. It's like a obscure paper. In fact, even 5 years later, when Albert Einstein followed up on it, and that's maybe 3 weeks from now, 4 weeks from now, I don't know. We'll see. We're in no hurry, right? As long as I don't die of a heart attack. So Einstein would present a paper that eventually won him the Nobel Prize, that basically supported Planck's solution to the ultraviolet catastrophe. What was Planck's solution? It was that maybe energy wasn't continuous from level 1 to level 2. Maybe energy only existed in little packets of energy. We might call them photons, or from Star Trek, photon torpedoes, Captain. Little packets of light or energy, photons. And it was a very simple formula. I don't know, maybe I can put it up here. Here it is. E equals hv, or actually it's E equals h nu, but it looks like a V to us English speakers. It's the Greek letter nu for frequency. But basically, it suggests that energy only exists in little packets of a constant, Planck's constant, h, times the frequency, nu, or V if you want. So that simple formula that Max Planck presented explained what took place with regard to, experimentally, with regard to black body radiation. Now, Planck didn't like it. Planck is an interesting soul. I feel sorry for him. I mean, he's what this book on the quantum moment suggests is that he basically survived by being low key, by not drawing attention to himself. When you're in a crazy world where people are being killed and so forth, you want to be a nobody. You want to be the person that nobody notices. You don't want to be, when the Romans destroy Jerusalem, you don't want to be in the intelligentsia, because if you are, you're the ones they're going to take back and kill in Rome. And so Planck kind of kept a low key. When he was a young man, I think it was the Prussians that took over his home state of Kiel. And then he lost 2 daughters who died in childbirth. His first son died in World War I. His second son was part of the plot to assassinate Hitler, and he was put to death in, I think, 1944. So Planck basically, he didn't want to be known. In fact, it's interesting, he was told somewhere, when he was doing his studies, not to go into the field of physics he did, thermodynamics, about heat and such, because pretty much everything, not to go into physics, because pretty much everything was discovered that needed to be discovered. But Planck didn't care. He was fine with being a nobody that nobody noticed. And then that's what he was doing, obscure little nothing in thermodynamics when he discovered this. And he didn't want to believe it either. He was a very conservative kind of temperament. He didn't like it. He found it distasteful. The idea that energy would not be continuous, because basically the quantum world, as it is unfolded, suggests that there is no infinite in this world. This universe doesn't know infinite. That even space is quantized. I would propose to you that there is not an infinite distance between Zeno's bow and the target. I think, by the way, I don't think the bow was what he had, some other illustration. But anyway, it may be a race or something. But there is not an infinite amount of space between A and B. There are little packets of space, as it were, that can expand and shrink, apparently, according to relativity. And similarly, there is not an infinite amount of energy between 1 and 2. There is 1, and it goes immediately to 2 on the bottom level of reality. Well, I hope this has been mildly amusing to you. Maybe you know these things already, but our journey into Schrödinger's course continues. And when I have a clearer sense of the ultraviolet catastrophe and how I want to approach writing this up, I do hope to write up not just Schrödinger's course, but Schrödinger's textbook, from Planck to Dirac. Well, this has been our weekly science, Quantum Saturdays, with Ken. I'm going to give you my historical pronunciation of my name. It's Skank.